prediction of solar events using vector magnetic fields, and machine learning. As we mentioned, one of the nice things about HMI data and all the data from SDO is that it's consistent in time with some interesting differences. And so Manolis is going to give us a talk here on this. Thank you, Manolis, take it over.
Thank you, Todd. Thank you for this opportunity to give you just a few thoughts about where we stand and what kind of questions we have to address and problems and issues in the future if we are to follow this approach of machine learning. So overall, as I don't have much time, I'll try to present an as coherent story as possible, starting with the question first. Why do we have to use machine learning for solar weather forecasting? We don't have to, but why is it beneficial? Then whether this vector magnetograph capability of HMI has led to any advances in terms of space weather forecasting, opportunities and challenges for machine learning applications, and finally a big issue, the interpretability in some machine learning, more precisely deep learning methods or unsupervised machine learning methods that appear to be trading performance for an understanding, a physical understanding. Okay, so the solar end of space weather, solar events, is something that has a varying heliospheric impact because of the directionality of two of the major effects, coronal mass ejections and solar energetic particle events. Flares, as you know, are just electromagnetic radiation, so there is no directionality issue here. But CMEs and SEPs do have one. So different vantage points within the heliosphere view a certain event differently. So all in all, if we had to start through the different problems of extreme solar events, major solar events, then we would start from solar flares because they just propagate with the speed of light. They are the first element that we see within 8 minutes, 8.2 minutes or so from occurrence on the sun. And then the question to ask is whether these flares are associated with coronal mass ejections or not. They are confined events in this case. In case there are coronal mass ejections, then we want to know the time of arrival of geospace and the geo-effectiveness of them. In case there is no CME, we care to know whether there are any beam events that are just propagating from the flaring location. If there is a CME, then we care about SEPs, solar energetic particle events at geospace, and the attributes of each one of these events so that to be able to assess the space weather significance that they have. So what we are talking about is an interconnected physical system, different physical systems that are intertwined. We have an immense volume and parameter space. We have about 8 orders of magnitude of spatial and temporal spanning. And as I said, there is interconnectivity. So this is all in all what we call, this is a modern term, more or less a big data environment. So because of this, because we wanted to address the big data part of space weather, there have been literally dozens of machine learning based papers in solar flare forecasting since 2007. Some papers in CME forecasting, although the bulk of work there refers to the prediction of the arrival time of CMEs at Earth. And there are some studies. This is just the start of studies of SEP events using machine learning. This is a very rapidly and dynamically evolving area of research over here, but there are some reference texts, such as a paper by Enrico Camporeale and company a couple of years ago, 3 years ago, that has different machine learning techniques for space weather. This is, as I said, a highly recommended text for that. So let's see. Before we start on machine learning, I'm going to give 3 definitions here that I think make sense. One is data mining. What is data mining? This is a term that you might have heard quite frequently. It is an essential part of knowledge discovery, and it pretty much means that we use some methods that have a certain intelligence, let's say, to extract meaningful data patterns. Then in terms of data mining, we can use machine learning, which tries to ask the following question. It tries to ask, how can we build computer systems that automatically improve with experience? And what are the fundamental laws that govern all these learning process? And then we have deep learning that's kind of trying to mimic the human brain. So it uses networks and tries to learn of data that are unstructured or unlabeled. So there is a big difference between machine learning and deep learning, in the sense that machine learning can be supervised and unsupervised, in which case we try to train on something for which we know the answer. Whereas in deep learning, we have unlabeled, so we do not really know what kind of features the code is focusing on before reaching an outcome. Okay, so in terms of solar weather, space weather, the solar end of space weather, these kind of applications, I am not even sure as we speak whether deep learning methods are appropriate, because there have been texts that express concern, such as this, for example, in which you would need millions of labeled examples to feed through a deep learning method to be able to have some acceptable performance here. So this could be a problem if we had to make pattern recognition in patterns such as these numbers over here, in which you try to identify different handwriting styles, but it may not be as appropriate for flares or CMEs or SEPs, in which case we're talking about a few thousand or several thousand events per solar cycle, or even 100 events in case of SEP events that are the upper tip, I would say, of solar-ended space weather. So the HMI has provided the SHARP database. Monica and companies several years ago, they have provided these 25 parameters. Because of the vector magnetogram capability, we have the lion's share of these parameters to be associated with vector fields. You can see them over there, 21 parameters out of 25. And then you only need one component of the field to derive the other 4 parameters. Monica and Sebastian Cuvidad tried in 2015 to try to predict flares using a relatively simple machine learning model, the support vector machine, that also allows you, like several other models, to rank the parameters in terms of significance in the forecasting outcome. In which case you can see over there that the vast majority of parameters, the ones that rank more highly, are the parameters that use vector magnetograms. On the left-hand side, you see a work by, again, Monica and Stathis Ilonidis in 2016, who tried to do the same thing with CMEs. Again, they had different rankings happening in there, but mostly relying on parameters from vector magnetograms. The important feature here is that if you change the forecast settings, like for example, the forecast window from 24 to 48 hours, then the ranking order changes as well. So this is kind of thing that, it's, as I said, it's an active area of research, and there are several open questions here, but we appear to be seeing a benefit by using parameters, metadata parameters, relying on vector magnetograms. Then in another effort in the EU, the European Union project FlareCast has been able to define a parametric space of, the final version of it is 209 parameters in there. From which the vast majority comes from HMI parameters. We have replicated SHARP parameters, and we have added quite a bit more. Again, the lion's share comes from the vector magnetogram-based parameters. And on the left, you see a recent study by Christina Campi and company, in which case they try to rank parameters by using 2 different machine learning methods, the hybrid lasso on top and random forests in the bottom. For flares, of class M and above. And you can see again that you have vector magnetogram-based parameters ranking pretty highly. The random forest test ranks entirely, the highest rankers are metadata parameters that rely on vector magnetograms. So machine learning appears to be helping us in this respect, but it's not a free lunch. It's neither a magic wand, not a panacea over here. In Christina's work in 2019, they tried the following test. They used some very strict training and testing works over there. What you can see here, let me get my laser pointer. What you can see over here is different methods, Monica's and Sebastian's method, then a method by a study by Florius et al. In 2018, that was a FLAIRCast study. And then for reference, a deep learning model by Naoto Nishizuka and company. The radius of each balloon over here corresponds to the number of parameters. So you can see that Christina has used a great deal of parameters more than the other studies. But nonetheless, it scores lower than that. And we believe this is because of the training and testing that were pretty strict. Because if you try to do it with, let me see, if you try to do it with, if you try to emulate the training and testing practices of Kostas Florius and Monica Bobra, for example, then you see all of a sudden the same method, the same parameter score higher than that. So you have to be careful about how you train and how you test the models. So in terms of training and testing, we think that what is useful here, and the HMI data, SARP in particular, data product, provide the opportunity to do it, because as already mentioned, we have a solar cycle worth of data, is to create what we call a benchmark data set. And this is an effort by the data mining lab at Georgia State University, in which case the entire cycle 24 has been partitioned in 5 different partitions. Why is that? Because we want to study, to train a certain model in one partition and test on another, right? So these benchmark data sets are pretty highly curated, high quality data sets. We are sure about this data, and we want to evaluate and, most importantly, compare different machine learning methods on the exact same conditions. Because if you just compare machine learning methods on different settings, different data and everything, just putting together the skill scores or the performance indices that they provide is not really of much meaning, I would say. So benchmark data sets can help us actually homogenize the training and testing. This was not the first effort, by the way, one by Graham Barnes in 2016, where we were predicting, the community were comparing rather different FLAIR prediction methods. Another one by FLAIRCast that's going to be out shortly. The API of FLAIRCast and the database will be free to the community within, I would say, the first half of this year, so imminently. And then, of course, we have the initial work with SDO, the heliophysics events knowledge base, with a number of features in there that could be used for this kind of purpose.
You have about 2.5 minutes left.
Thank you, Todd. All right, so there are major challenges. Of course, we are talking about different occurrence frequency, different climatology that have to be taken into account, and we don't have an answer yet. We have the class imbalance problem that has is another big issue, because machine learning methods tend to work on balanced samples. So we believe we are not unleashing the full potential of these methods if we have class imbalance data sets. And then how to identify and use time series in there. There are works, like for example, a very recent work, which is in press in ABJ supplement series by Azim Ahmadzadeh from Georgia State, in which case we try different methods for the class imbalance problem. And then, of course, we have to be careful what kind of verification methods we are using. For example, in a class imbalance problem, if we are talking about accuracy, then we, again, do not mean anything in particular, because whatever is accuracy over there, which is the ratio of correct predictions over total predictions, degenerates to 1. So if you see any method saying that I have a 99.95% accuracy in a class imbalance problem, don't believe them too much. If you do not have class imbalance, then you have different indices agreeing with each other, coinciding with each other, like the true skill statistics and 2 versions of the Heidke skill score over there. So there is a toolbox that has been inherited to us by different communities, most importantly, the weather community, terrestrial weather. We have to make sure that we know what we use, and we have to make sure that we use the right metrics. Okay, then another thing has to do with using a benchmark data set to expand horizontally and vertically, so that to include more problems in there, like this attempt by Yannis Kontogiannis through Flarecast, in which case we see a couple of features, such as the non-neutralized currents and the polarity inversion line correlating highly with CME speed. So in essence, you have to be self-consistent in trying to expand, but benchmark data sets are actually offered for this kind of expansion. There are uncertainties if we are just expanding from flares to SCPs, and this is a very, very active area of research, so this is a whole, different talk, different presentation here, but just to let you know that there are efforts, in which case, through self-consistently expanding data sets, we can do that. Okay, and finally, as I mentioned before, do not use machine learning, unsupervised or deep learning, because we do not know why it works. And I have a nice example over there. So that's my final slide over here. What did I say? I said that there are benefits in machine learning, and there are indeed benefits by using vector magnetogram parameters. There are, at the same time, there are challenges that we have to deal, such as training and testing, the class imbalance, variable climatology, and performance verification. We need benchmark data sets that are scalable and expandable, self-consistently speaking. So there are uncertainties that we need to be constrained, and this is case by case. So I do not think there is a common kind of treatment for this kind of problems. And finally, interpretability. For us, it is crucial, because we want to understand besides predicting, but some user communities, they couldn't care less about what we understand in terms of physics. If a method works for their purposes, then that's all they need to know. And that's all I have to say. Thank you very much.
Thank you, Manolis. Excellent talk. It's interesting to see all of the different options and how we're learning things. But it's not always as straightforward when you have a tool, and I think we're all learning a little bit how to do it. I'll just note that there is a Drive Science Center called Solstice out of the University of Michigan, that is learning to apply machine learning techniques to a range of problems across heliophysics, including predicting space weather, but also getting into some of the other aspects of it in terms of the ionosphere and predicting what's happening in inversions and using it for a variety of things. So there's a lot of people, of course, working on this, and it's a very popular topic. It's delightful to see that the consistent data from HMI is so useful. Do we have any, and also we mentioned that there is a Space Weather Trek at Colorado that is being led by Tom Berger. So that's another group that's working on machine learning things. We have a comment from Vishal Upandran. So if anyone's interested, we applied a GradCam technique to understand the sources of fast and slow solar wind learned by a deep learning in solar wind forecasting model. And there's a link.
That's a good idea. There are some interesting results by this method. That's why I provided an example. What is open in my mind, at least a question mark, is that we don't know what is mostly responsible for their results. Pretty much like we can do parameter ranking if we are using supervised machine learning to find out how they work. So that's the key thing here. And as I said, it's crucial for us, but it may not be that crucial for other communities.
We have a question from Masha. Do current machine learning methods take into account proximity to other active regions? And then similarly, what time-dependent parameters are currently being used? So things like emergence and cancellation.
Right. So time dependence is a crucial factor as well. Machine learning methods are naturally suited to use time series, but we have to be able to use them in a way that makes sense. If you have, for example, a forecast time step that is much smaller than the length of the time series that you use for training, then if you go step by step, you actually have to deal with a nearly identical time series. So you get a clustering, which is kind of artificial into your parameter space, and you have to go through it, and you have to find ways to go around it. So it's indeed a very valid question, but these are all challenges that I think we do not have a clear answer yet, and the community is working on that.
Great. Well, thank you very much for your talk. Appreciate it. Our final talk of this session is going to be